Welcome back to our last lecture for Physics 102. This week we will be covering chapters 24 and 25 on magnetism and electromagnetic induction. Here's a list of the topics we'll talk about in chapter 24, dealing with basically magnets and how electric currents relate to magnets. Essentially, the force between any two charged particles depends on the magnitude of the charge. So if you remember in past lectures, we've talked about electrons have a negative charge. And so the force between particles and essentially between magnets depends on how much of that charge you have and how far apart the charges are. When the charged particles are moving, the electrical force between the electrically charged particle also depends on their motion. So the force depends not only on the charge and the separation, but also on their motion. There is a force due to the motion of charged particles that we call magnetic force. So magnetic force, you see that force in when you put like a pair of magnets and two things or two magnets hooked together, and you can either have attraction, things can attract each other, or you can have repulsion where things push apart. So magnets can pull together or they can push apart depending on what end you're holding together. So magnets have things called poles, which we'll go over in just a little bit, essentially a north pole and a south pole, and the opposite poles will attract. So if you hold like a north and a south together, they'll attract, and the same poles will repel. Magnetic forces behave really similar to electrical forces. So just like in the atom, protons and electrons attract each other because they're opposite forces, and like electrons and electrons or protons and protons will repel each other because they're the same force. The amount of magnetic force depends in part on the distance between the two magnets. So the strength of that interaction between the magnets is stronger when they're closer together and weaker when they're further apart. So I'm guessing all of you have played with magnets at some point, and seen how when you put two magnets close together, they kind of appear to pull in and hook together. So for example, these, like the Thomas train cars here, if you have them this far apart, there's that magnetic force there still between them, but it's a weaker force since they're further apart, and it's not strong enough to actually move the cars. But if you were to put them, say like a centimeter apart, then the magnetic force is strong enough that it will pull those two cars together and the magnets will hook together. Every magnet has two poles, and they call it a north pole and a south pole because the north pole, like if you look at a compass, that's the north-seeking side, and the south pole is the south-seeking pole. And if you put magnets together, I'm guessing you've all done this at some point, the north and the south poles of the magnets will stick together. And if you try to put like a north and a north, similar poles, they will repel. So like poles repel and opposite poles attract. And you can't have a magnet with just one pole. So you can't like cut the magnet in half, and you can't make a cut like here and say that you're going to end up with a north magnet and a south magnet. You're always going to have a north end and a south end on the magnet. So in a bar magnet here, you have the north and the south on opposite ends. In a horseshoe magnet, really you still have the north and the south on opposite ends. It's just been, the magnet has been bent so that those two ends are closer together. Magnetic field shows us the strength and direction of the magnetic force around the magnet. So you can see in the picture on the right there, you sort of see these circular lines going out around the magnet from this metal here being attracted to the magnet. And you can see with your magnetic field, you see the direction those particles are moving, and we show by convention the direction from the North Pole to the South Pole. And so we show that with an arrow, and that's based on the motion of the electric charge in the atom. So that's the the movement of that electric charge. So we have the arrow going from the north to the south, and the strength of the magnetic field is indicated by the closeness of lines. So lines that are closer together, as in right here, that shows a stronger magnetic field, and lines that are further apart show a weaker magnetic field. Magnetic fields are produced by two things. They're produced by the electron spin, so the electron spinning around like on its own axis, and electron revolution, the electron spinning around in a circle, so around the magnet. So magnetic fields, again, are produced by two kinds of electron motion, electron spin and electron revolution. And the spin is the main contributor to magnetism. So that's the main thing giving us that magnetic force. And if you have a pair of electrons spinning in the same direction, you'd have a stronger magnet. A pair of electrons spinning in opposite directions would cancel the magnetic field. So let's do a review question here. The source of all magnetism, is it electrons rotating around an atomic nucleus, electrons spinning around an internal axis, either A or both A and B, or sorry, either or both A and B, or tiny bits of iron? And the answer is either or both A and B. Another review question, where magnetic field lines are more dense, is the field there weaker, stronger, both weaker and stronger, or neither weaker or stronger? And the answer is stronger. So again, the closer those lines are together, the stronger the magnetic field. The further apart the lines, the weaker the magnetic field. So there is a connection between electricity and magnetism, and they used to think that there was not a connection between that electricity was one thing and magnetism was something completely different. But at some point they realized that these two things are connected. So magnetic field forms a pattern of concentric circles around a current carrying wire. So if you were to have this rod here, and you see this in the video coming up, if you were to have this rod here that has electric current running through it, and you were to put compasses around that, you would see the compasses all line up in relation to this electric current. And so they realized that electric current can act like a magnet, pulling those magnets in a certain direction. When the current reverses direction, the direction of the field lines reverse as well. So if you were to change the current, going from this way to going down this way, then your compasses would change and they would flip over and turn the other way.
The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there's an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? Bam! All the compasses will line up with the field. And it turns out that field takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current-carrying wire is a magnetic field that takes the direction of the concentric circles.
So the power from electric current and the force of magnetic fields can be combined to make something called an electromagnet, which can have very practical and useful applications. An electromagnet is a current-carrying coil of wire. So you have a piece of wire that's coiled and it has a current going through it. The strength of the electromagnet, so essentially you're creating a magnet by running electricity through a wire, and the strength of that magnet you've created can be increased by increasing the current through the coil. So let's say you were to have just like a straight wire or a single coil. You could increase the current going through that, and that would increase the magnetic field force, or you could increase the number of turns in the coil. So every coil that you add increases that magnetic force. An example of electromagnets are some high-speed trains, and the way the electromagnets work on the train is the train first gets levitated above the track slightly by some magnetic coils that run along the track called the guideway, and these magnetic coils are repelled by magnets on the underside of the train. And so if you remember, opposite or like poles repel each other, so it's two like poles, and you're essentially repelling the train from the track just slightly. So the train is lifted and essentially is riding on air. Power is then supplied to those coils within the guideway walls, and they propel the train by continually alternating the electric current fed to the coils. So first there's a magnetic field that's alternated that pulls the vehicle forward a little bit, and then the current alternates, and then there's a magnetic field further back that pushes the train forward, and the train keeps getting pulled forward and pushed forward, that current alternating back and forth, creating a push-pull very, very quickly, which produces a forward thrust moving the train forward. And the good thing with these trains is there's no friction and no bumps, so it's a very smooth ride, and you eliminate friction since the train is literally riding on air. Let's do a review question. An electromagnet can be made stronger by increasing the number of turns of the wire, by increasing the current in the coil, both of these, or none of these. The answer is both. So again, if you increase the number of coils and the number of turns in the wire, or you increase the current in the coil, you'll make that magnet stronger. If you have a current of charged particles moving through a magnetic field, so for example, a wire with a current going through it, and those electrons, originally your wire was here through the magnet, those electrons are moving through a magnetic field, those electrons will experience a deflecting force, and the direction is perpendicular to the magnetic field lines in the current, so essentially perpendicular to the wire. And if you have the current moving one way, the wire will get deflected up. The current carrying wire, if you were to switch the current and have it pull the other way, the wire would get pulled down. You'll see this example of this in the video on the next slide. And the force is strongest when the current is perpendicular to the magnetic field line. So if you were to put it in another angle, this deflecting force will not be as strong.
I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? See, it's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up And the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current-carrying wire, boom, being deflected in a magnetic field. Period. That's it.
If you want to measure the amount of current going through a wire, you can use something called a galvanometer, and it's a current indicating device named after Luigi Galvani, and it's called an ammeter when calibrated to measure current in amperes, and it's called a voltmeter when it's calibrated to measure electric potential in volts. So if you remember, the voltage is electric, that's the potential, and the actual current going through, we measure in amps or amperes, and so it may be called an ammeter or a voltmeter. These are two types of galvanometers. So if you were to take the setup here on the right and you were to just run a current straight through this setup, you would cause this loop to flip and rotate depending on which way the current went through. So it might flip so that, you know, this end moves down to north and this end, or this end moves down to south and this end up to north. If you were to put the current going through the other way, the loop would rotate the other direction. So if you continued the current going through one way, this rotating, or this loop here, would just stay with one end on north and one end on south. And electric motor uses the concept that if you alternate that current, you change that current back and forth and make it go in opposite directions, then this loop will continue to rotate in a cyclic fashion and produce continuous rotation. And this is the basis for your electric motor. So the Earth itself is actually a huge magnet, and you have the magnetic poles of Earth. So the magnetic poles are, you know, you have your North Pole here and your South Pole here. They're not the same as the geographic poles, which you'd have your North Pole right here and your South Pole right here. They're a little bit off from that. But the magnetic field of Earth is not due to a giant magnet in the interior. So it's not like the core of Earth is just a giant magnet. It's due to electric currents. So as you can see here, there's electric currents moving throughout the Earth and moving around the Earth here, these electric currents. And most scientists think that moving charges looping around within the molten part of the Earth create the magnetic field that you see around the Earth. So the Earth's magnetic field does reverse direction, and it's had 20 reversals in the last 5 million years. And that would mean that the magnetic field, you know, instead of going from north to south, would flip over and go from south to north. And the universe is a shooting gallery of charged particles called cosmic rays. And cosmic radiation is very hazardous to astronauts. Cosmic rays are deflected away from the Earth by the Earth's magnetic field. So if you didn't have the magnetic field, these cosmic rays, which would be hazardous, could get to Earth. Some of them are trapped in the outer reaches of the Earth's magnetic field and make up what they call the Van Allen radiation belts. Storms on the sun, we learned a little bit about the northern lights earlier, but storms on the sun hurl charged particles out in great fountains, and many of these pass near Earth and are trapped by the Earth's magnetic field. The trapped particles follow corkscrew paths around the magnetic field lines of Earth and bounce between the Earth's magnetic poles. Disturbances in the Earth's field often allow the ions to dip into the atmosphere, causing a glow. So again, these are a plasma. So we have solids, liquids, gases, and the plasma. And then we get the aurora borealis or the aurora australis. Now, magnetism is also seen, it's seen in lots of different ways within your body. But some animals can use biomagnetism to help, like a compass, to help them know where to go. So some bacteria have grains of magnetite, and it's a compound that's equivalent to iron ore, that they string together to form an internal compass. And they use these compasses to detect the dip of the Earth's magnetic field. And this gives them a sense of direction and helps them locate food supplies. Pigeons also have multiple domain magnetite magnets within their skulls that are connected with a large number of nerves to the pigeon brain. So pigeons essentially have a magnetic sense, and not only can they discern longitudinal directions along the Earth's magnetic field, they can detect latitude by the dip of the Earth's field. So other similar animals that use this magnetism to help know where to go are bees, butterflies, sea turtles, fish. So if you wonder how animals know where to get from place to place, part of it is through magnetism. So that's the end of chapter 24. We're going to move on to chapter 25 next, which is on electromagnetic induction. So our topic for chapter 25 is called electromagnetic induction. And this concept was discovered by Faraday and Henry. They both discovered this process in separate locations. And electromagnetic induction, sometimes we just call it induction, is basically a process where when you move a wire past a magnet, or a wire or a magnet past a wire, it produces voltage across the wire. And if you remember, voltage is that electric potential, and essentially it causes a current to move through the wire. So on the picture on the right, they're moving a magnet through this wire coil, and it produces an electric current through that wire. It's said to induce the current, and that's why we call it electromagnetic induction.
This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone was excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries over there, gang. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything? No. Faraday didn't see anything either. Okay. Okay. And but watch this. Henry didn't see anything either, but watch this. Did you see something? Yeah. Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, no lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed, and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles, honey. The candle industry was furious later on, okay? Because what he did is he went down and he took 2 wires, and guess what happens with 2 wires, gang? 2 twice as much current. Goes back to bed. Then he thinks, I wonder 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder 1,000,000 wires. What do you think? 1,000,000 times as much. Okay? This was a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire. Doesn't even have to be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now this loop happens to be a copper wire, so the voltage in that produces a current. So look at this. You get a current. Change the magnetic field in 2 loops of that closed copper wire, 2 loops of that circuit, and guess what you get, gang? Twice as much voltage. 3 loops, 3, da-da-da-da-da. So that's the rule. All you got to do is change the magnetic field intensity, and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice. Now we can produce electricity. So you know how all of Europe started converting to electricity. They started having lamps and all that stuff, and they had all these kids up on the hills going like this. Okay? And these kids are all doing this thing, okay? And one day they say, hey, we're getting tired doing this. See that waterfall coming down? Why don't we put this wire on a great big piece of wood and have it rotate, huh? By the waterfall, put a little paddle wheel, and we'll go home and get all electricity. And that's, of course, the start of the Industrial Revolution. I'm making that part up, but you get the idea. All you got to do is rotate the loop in a magnetic field, or just plop in and out of the magnetic field, and there's your electricity. Faraday's law.
So as you just learned in the video, the voltage can be, which is going to increase the current going through the wire, can be increased by increasing the number of loops of wire in a coil, or increasing the speed of the magnet entering and leaving the coil, or the speed of the coil as it enters and leaves the magnet. So as you remember in the video, as he moved the wire very quickly up and down through the magnet, he increased the voltage, and he also increased the voltage a lot when he increased the number of loops. Slow motion produces hardly any voltage, as you saw, and rapid motion produces a greater voltage. Voltage will be induced in the wire loop, whether the magnetic field moves past the wire or the wire moves past the magnetic field. So, so you can move the magnet up and down, or you can move the wire up and down. And really, you're doing the same exact thing. Either way, you're going to induce the voltage and induce the current to move through the wire, whether the wire is moving or whether the magnet's moving. And as we just mentioned, the more coils that you have, the more voltage that you will produce as you move the wire and the magnet past each other. So if you have twice as many loops, you're going to have twice as much voltage. If you have 3 times as many loops, you're going to have 3 times as much voltage. So Faraday's law, one of the people, again, who discovered electromagnetic induction, his law states that the induced voltage in a coil is proportional to the number of loops, multiplied by the rate at which the magnetic field changes within those loops. So again, you're dealing with the number of loops, and you're dealing with the speed at which the magnet and the wire are moving past each other. The amount of current produced by electromagnetic induction is therefore dependent on the resistance of the coil, the circuit that it connects, and the induced voltage. It's more difficult to push a magnet into a coil with many loops because the magnetic field of each current loop resists the motion of the magnet. So if you were to try to push a magnet through a whole lot of coils, it would become increasingly more difficult the more coils you had. So the resistance you feel when pushing a piece of iron into a coil, does it involve repulsion by the magnetic field you produce, energy transfer between the iron and the coil, Newton's third law, or resistance to domain alignment in the iron? And it's a repulsion by the magnetic field that you have produced by making all those coils. Voltage induced in a wire requires changing magnetic field in the loop by moving the loop near a magnet, moving a magnet near a loop, or by changing a current in a nearby loop. So Faraday's law, again, which states that increasing the number of coils will increase the voltage. There's some practical applications to this, and one you'll see in the next video is that activation of traffic lights, that traffic lights are activated by a car moving over underground coils of wire. There's also the triggering of the security system at the airport by altering magnetic fields in the coils as one walks through, scanning magnetic strips on the back of credit cards, recording of sound on tape, and electronic devices and computer hard drives and iPods.
Hey, you know what? You know what is a neat application of electromagnetic induction? It's just been the last few years, and that's the smart lights. When you're traveling down the road and you're coming to the traffic light and the lights change for you. You drive over something and that something changes the lights. They used to put like a piece of rubber tubing out there with compressed air, and it would boom, make a little pulse of air, and that changed the light, but then the rubber would wear out. What they do now is they bury in the road a coil of wire. Okay? Coil of wire buried in the road. Now, through that coil of wire is a magnetic field of the Earth. And part of that field is in that Earth, all right? Now, if you could change the magnetic field intensity of the Earth through that big coil of wire, what would you induce in that coil? Begin with a V. A voltage. Isn't that right? So when your metal car drives, when your iron car, a wooden car won't work. When your iron car goes over that coil of wire, does it not alter a little bit the magnetic field intensity in that loop? Answer begin with a Y. And when it does that, it makes a little tiny electric current which activates the switch of changes the lights. Isn't that neat?
Review question here. More voltage is induced when a magnet is thrust into a coil. Is it quickly, slowly, both, or neither? And more quickly. So the quicker you thrust the magnet into the coil, the more voltage you will get. Another question, not only is voltage induced when a magnet is thrust into a coil of wire, but is it current is also induced, energy is also induced, power is also induced, or none of the above? And current. So voltage induces current. So don't say energy or power, which are conservation of energy no-nos, because you can't induce or create power. You can't create energy. Energy can be transferred but not created by induction, but current is created. Generators and alternating currents. A generator is the opposite of a motor, so it converts mechanical energy into electrical energy via coil motion. So it produces alternating voltage and current. So similar to your similar setup, as you can see here, to your motor, but it has mechanical input causing the loop to rotate, and you get electrical output out of it. So the exact opposite as your motor, you have electrical input coming in and you get mechanical output. So using Faraday and Henry's discovery of electromagnetic induction, Nikola Tesla and George Westinghouse showed that electricity could be generated in sufficient quantities to light cities. So imagine this discovery, this application of all this work they'd done on electricity, having a very practical application. An MHD, or magneto-hydrodynamic generator, eliminates the turbine and spinning armature altogether. So a plasma of electrons and positive ions expands through a nozzle and moves at very high speeds through a magnetic field. The motion of charges through a magnetic field gives rise to a voltage and a flow of electron or flow of current as per Faraday's law. A transformer has an input coil of wire. The primary powered by AC voltage source, and an output coil of wire, the secondary connected to an external circuit. Both are wound in a common iron core, so the magnetic field of the primary passes through the secondary, using an alternating current and voltage in one coil to induce an alternating current and voltage in the second coil. Transformers can be step up or step down voltage, and a step up transformer produces a greater voltage in the secondary than supplied by the primary, and the secondary has more turns in the coil than the primary, or a step down transformer that produces a smaller voltage in the secondary than supplied by the primary, and the secondary has less turns in the coil than the primary. So essentially you can, with a transformer, you can increase or decrease voltage. The transformer relationship is the primary voltage divided by the number of primary turns is equal to the secondary voltage divided by the number of secondary turns. A transformer transfers energy from one coil to another. The rate of energy transfer is called power. Power into the primary equals power into the secondary, or voltage times current of the primary equals voltage times current of the secondary. A transformer transfers energy from one coil to another. So for example, a voltage is stepped up before leaving a power station. Voltage is stepped down for distribution near cities by cables that feed power to the grid. Voltage is stepped down again before being supplied to businesses and consumers through substations. So let's do a review question. A step-up transformer in an electrical circuit can step up voltage, energy, both A and B, or neither A and B. And the answer is voltage. So stepping up energy is a conservation of energy. Again, you can't create energy, but you can create voltage. An efficient transformer in an AC electric circuit can change current, energy, power, or all. And the answer is current. Let's look at self-induction next. In current carrying loops in a coil interact not only with loops of other coils, but also within loops of the same coil. So each loop in a coil interacts with the magnetic field around the current in other loops of the same coil. And this is called self-induction. When a switch is opened, the magnetic field of the coil collapses. The sudden change in the field can induce a huge voltage. Almost all electrical energy sold in the world today is in the form of AC because of the ease at which it can be transferred from one voltage to another. Large currents in wires produce heat and energy losses, so power is transmitted great distances at high voltages and low currents. Power is generated at 25,000 volts or less and is stepped up near the power station to as much as 750,000 volts for long distance transmission. It is then stepped down in stages at substations and distribution points to voltages needed in industrial applications, so often 440 volts or more, and for the home, 200 and 120 volt. So in Faraday's law, we see that an electric field is induced around a region of space where a magnetic field is changing with time. And Maxwell found that if electric charges are set into vibration in the range of the frequency that match those of light, waves are produced that are light. So that's the way that you get this electric and magnetic field to work together to produce light. The mutual induction of electric and magnetic fields can produce is it light, energy, sound, or none of the above? And the answer is light. That's the end of our new lecture material. Congratulations on making it through the course. The only thing that you should have left next week is to complete your final and then complete any late work that you might have. You can take the final whenever you're ready. I would recommend that you review your chapter homework before you take the final. And I also have chapter review slides available, or lecture review slides available for you to go through, which review everything that we've covered in the course. You'll have till Thursday of finals week to complete your final. Just keep that date in mind. A lot of students get confused with that since usually our tests are due and everything else has been due on a Sunday. So that finals week, you'll have your final due by Thursday at 11:59 p.m. And also any late work that you need to get done needs to be also done by Thursday of finals week. I'll be submitting grades on Friday, so that's why it's important to make sure that your assignments get done Thursday night. It's been great having you all in the course. I wish you all the best as you go on from here. And please let me know if you have any questions as you're going about submitting these final assignments, or you have any questions about your grade as we wrap up the course. Best of luck in all your finals, and again, wish you the best as you go on from here.